That's why it was a problem.
Yeah, no problem.
Waterloo Station. If you degrade the resolution, let's say this one was 25 centimeter, but if you go to, let's say, 5-meter resolution, 10-meter resolution, and 20-meter resolution, you can go beyond 20-meter, but you can say in the 20-meter also we are losing the target information somehow, the texture and the scatter. So somehow many scatters are, let's say, combinedly giving information in one pixel, and we are somehow not able to separate them together. So the important factor here is the, let's say, we need a good resolution, and that's why we do the synthesizing kind of thing. The synthetic aperture is being formed because of that only. Now, let's talk about the resolution. As I said, in the SAR image, the resolution is one of the important things. So let's say the SAR image is conventionally it is two-dimensional. So we have range dimension and azimuth dimension, and every let's say every image, it's set of pixels. If you zoom in, you can find the pixels here. Let's say if I'll zoom in this area, you can see, and now you can actually visualize that, okay, it is a collection of pixels, and every pixels has the size in, let's say, range direction and azimuth direction, and that is straightforwardly called as a range resolution and azimuth resolution. So range resolution is something that is smallest distinguishable distance between the two objects in, let's say, in along the radar line of sight. That's in the range direction, and in it should be in across, actually, in the okay, no, in the line of sight. And azimuth is in the direction of the flight. That means the satellite or the airborne SAR moves in one of the way, and it is looking side in a side, let's say, look. And in the movement direction, what resolution we have is the azimuth one, and in the look direction, what resolution we have is the range one. So range resolution straightforwardly depends on the bandwidth. If you have a larger bandwidth, wider bandwidth, you can have a better range resolution. For example, I've added some of them here, some of the satellites example here for the Sentinel. You can see here, if you have a wider bandwidth, the resolution is very sharper. If you have a degraded bandwidth, you will have a, like, let's say 50 megahertz for the RISAT one, radar imaging satellite, you have a resolution of something like 3 meter. So this is very, let's say, straightforward formula. And in the range direction, we can actually play with the architecture, and we can achieve somehow, let's say, very good resolution. But in the azimuth direction, it's not the condition. The condition is not that straightforward. In azimuth direction, let's say if you're not doing the synthesis process, if you're not going for the synthetic aperture radar, and you're relying on the real aperture radar system, real aperture, let's say, antenna system, in that case, the formula for the resolution is something like lambda r by d. Now here, lambda for sure is, let's say, restricted based on the atmospheric condition and also the application what you're using. Like if you need to penetrate through the ground, soil moisture estimation and all, you will be looking for the L and C band. But if you do the defense related applications, what you'll do, you'll go for the X band. So obviously based on the application also, it depends that what frequency, and corresponding to that, what, let's say, wavelength you're using. Now, range is also somehow fixed because you situate the satellite somewhere in, let's say, in LEO orbit. For example, for Umbra, that the height is something like 540 kilometer from the ground. And that is also somehow fixed. So what you can change to get the better resolution, that's the D. Now, D is the, let's say, antenna aperture size somehow. Length that cannot go beyond certain level. For example, if you want to not do the synthesis process and you just want to rely on the real scenario, if you have a smaller antenna, something like what we use in, let's say, NISAR. NISAR had something like 10 to 12 meter of the antenna aperture length. And in that case, if you'll not do the synthesis, you'll reach to the resolution of something like 1.5 kilometer. That's huge. You can imagine that one pixel will have will be covering the size of 1.5 kilometer. All the buildings will be, all the, let's say, station will be covered in one pixel only. So that's not good for us. It's very coarse resolution. Now, let's say you want to actually reduce it somehow, the antenna size. As I said, the antenna size has a resolution expression dependency. So if you let's say in other example, if you have an antenna size of 5 kilometer, you can reach to 3.1 meter resolution. Now, again, 5 kilometer size of antenna in space is not feasible, right? You cannot do that. 5 kilometer is very long. Even for the airborne or the spaceborne, it is not possible to situate that size of the antenna, especially in three-dimensional space. So, and if you want to achieve something like this much of resolution, which we have seen in the previous image, you need 62-kilometer long antenna, which is nearly impossible, right? So the solution is to not go for the longer antenna. Instead, you can use the smaller antenna and synthesize the aperture by doing the synthesis process. That's called synthetic aperture radar, where you actually try to capture the information from different point in space. You are in all the instances, you are acquiring, let's say, certain point, and you are post processing them, doing the signal processing stuff. And in the range direction, usually the range direction is being controlled by the bandwidth. The range bins will be stored in one dimension, and azimuth, the acquisition from the different points, will be stored in the other direction. And you will do something like FFT, and there are different methods. You can do polar format algorithm are there, back projection are there. These are the methods you use to do the synthetic aperture. That's why we need to do the synthetic aperture to have higher resolution in the image without going for, let's say, a bigger size antenna, right? So that's a very brief introduction about the synthetic aperture radar. The signal processing of let's say of SAR is one of the different topics, which I'm not going to cover here, but it's very interesting and very fascinating. Now, let's say briefly we'll try to understand the polarimetry in SAR, that how actually different polarimetric configuration-based synthetic aperture are acquiring the information, different channels of the information from the ground. I usually quote this thing that every scatter or every target on the ground, let's again start from, let's again talk about the same image, that every target on, let's say, on the ground has their full polarimetry inherent into it. Means it holds the full polarimetry information. Something like I have written here, it contains the full polarimetric information, that is in terms of scattering matrix, where all the channels are there. Now it's on the capability of our system that how much it can acquire from there. So if you, for example, if you have a single polarimetry, you can acquire either this component or this component. If you have a dual polarimetry, you can acquire either either this component or these two components. If you have a compact polarimetry, you can have a combination of these things. So, but it depends. So that's why we call scattering matrix is a properties of target, not a properties of system. System needs to be capable of acquiring as much as information, and also it depends on a lot of things like the PRF, how you are maintaining, and the swath coverage, and based on the application you do the things in acquiring the polarimetric. So starting from the conventional single synthetic aperture radar, which was, let's say, single polarimetry, where what we are doing, what we usually do, we transmit one polarization and we receive one polarization. It has to be same. Like either you can go for the H, transmitting H, receiving H. So you'll be acquiring, instead of SHH, you'll be acquiring SVB, or you can transmit H and receive. Same sense of linear polarization will be transmitted, and same sense of linear polarization will be received. So you receive the information in terms of backscattering coefficient. You can have these two information in your out of the whole, let's say, scattering matrix. Now you can realize here that okay, the target has all the information. So target is kind of a vector. A target associates vector information in itself, but the conventional SAR systems were capable of just let's say acquiring the scalar information about it, either this one or this one. So obviously we are losing some of the information here from the target. That's why it was very difficult with the single polarimetry to characterize all the targets, to do a lot of stuff, let's say SAR applications by using single polarimetry. And that's why the researchers have switched to the full polarimetry mode, where they try to acquire all possible information from the, let's say, by using the synthetic aperture system. So in that case, if you compare these two, in that case, you need to transmit two pulses in one time slot. That obviously it has to be interleaved. You have to transmit H, receive H and V. You need to wait for that, and then you can transmit V. Otherwise, if you simultaneously transmit H and V, the system will be confused that the backscattering is coming from corresponding to H or V. So it has to be interleaved. So you transmit H in one time slot, you transmit H, you receive H and V, then you transmit V, receive H and V. So something like the wait time and here's a problem in the swath coverage area. Means the wait time is reduced, the swath coverage area becomes half, and that's why you need more time to cover all globes. It's something like the satellite revisit time will be doubled. For example, if in almost in for example in single polarimetry, if you are covering the same point, let's say you are revisiting the same point on the Earth in 12 days. In full polarimetry, you have to take 24 days to revisit the same place almost. So it's something like not good for the monitoring purpose. Like if you need to monitor something like oil spill or which actually being spread with the time, and that can cause widespread damage if you just wait for 12 more days. So what you need as quick as possible the let's say the acquisition, the revisiting, and that's why the revisiting time has to be shorter. So now there are two things: the revisit time, and the second thing, the second important thing is the polarimetric content, how much you have acquired. That is also important to completely characterize the target. So in between these two, let's say there was a trade-off between these two, and the researchers has let's say came to the solution that okay, we can do this thing, that we can transmit one polarization and receive two orthogonal polarization, so that the in one time slot we are transmitting one polarization, we are retaining somehow the swath coverage area, and we are also acquiring some of the polarimetric information. For sure, this polarimetric information will not be equivalent to full polarimetry, but somehow much better than a single polarimetry. Now, this slide gives the example of hybrid polarimetry condition where we are transmitting right-hand circularly polarized wave and receiving H and V. But there could be many possibility that you are transmitting one polarization and receiving orthogonal polarization. For example, I've listed some not some of them, all of them here, which has been discussed theoretically, and also some of them are practically implemented. For example, let's say dual polarimetry. What we do, we transmit one either of H and V and receive H and V as an orthogonal polarization. Now, Sentinel-1 is the satellite which is using this, and we have all freely available data for this satellite. That's one of the interesting data sets we have because it gives the temporal data, and you can do the interferometry and a lot of stuff. And the other, let's say, set of methodology which was discussed was the compact polarimetry mode, where the combination of transmission and transmitted wave and received wave are somehow different, not the same. For example, in the case of pi/4, this was actually proposed, this idea was proposed in 2005. I don't remember. I don't think this has been realized in, let's say, practical scenario, especially for the spaceborne. We have not seen any data of this. So it was proposed by Soares in 2005, which says that you need to transmit the 45-degree incline linear polarized wave, something like this, and you receive H and V. The other idea was proposed in 2006 that says dual circular pole, where you transmit circular and receive circular, transmit either of LHCP or RHCP, and then receive the orthogonal of these two. Then in 2007, Rane has proposed one of the idea that is called hybrid polarimetry, because it transmits circular polarization and receives orthogonal polarization. That's why the name hybrid came here. So in this case, either of circular polarization, a circular polarized wave has to be transmitted, and you receive H and V orthogonal linear polarization. This is the configuration has been shown here. In this case, you receive the information, or you store the information in terms of Jones vector, which is RH. It's somehow combination of HHVV and HHHV, and RV is combination of VVVH. This concept of hybrid polarimetry has been realized by many different satellites. Talking about the lunar surface exploration, NISAR and mini-RF was launched in 2008-9. That was on board Chandrayaan-1 mission. Then RISAT-1 was the first Earth observatory satellite-based hybrid polarimetry as mode-based satellite, and that was also launched by ISRO. Then ELOS-2 RCM, NISAR is just now launched, and we are waiting for the data. And it also has some of the area where it is going to acquire the compact hybrid polarimetry, not just compact hybrid polarimetry, specifically of the compact polarimetry. So the focus on hybrid polarimetry has its let's say merit, because hybrid polarimetry has a benefit over these other configuration. For example, if you have a pi by 4 mode, that's a linearly polarized wave, and you're transmitting the linearly polarized pi by 4 inclined wave. So if you have a target which is, let's say, perpendicular to this transmission, this transmitted pi by 4 linear polarized wave, you can probably miss the target, or the backscattering will be very weak. Means it is rotation selective. Like if you have, let's say, if you're transmitting the, let's say, pi by 4 oriented wave, and the target is inclined in this way, just orthogonal to this, the backscattering will be very weak. Similarly, for dual pole, if you are transmitting H and V, the acquisition will be orientation dependent. If it is in line with the transmitted wave, in line with the polarization of the transmitted wave, the backscattering will be very strong. But if it is perpendicular, the backscattering will be very weak. And if it is inclined in some other way, the dependency will be there on the, let's say, orientation. So to avoid this dependency, what you can do, you can transmit circular polarized wave. So if you have a circular polarized wave in any orientation, if the target is there, you can have relatively same strength of backscattering information. Now, in these modes, like dual pole mode and dual circular pole mode, there's a problem of crosstalk and ambiguity effect also, because always we know that the let's say co-polarized channel has a stronger intensity, 3 to 7 dB stronger intensity than the cross pole. So if you're doing some mathematics, like you're adding or subtracting the cross pole with the co-pole, we usually do that. In case of dual pole, where you have HH and HV, or VV and VH, one will be very stronger and one will be very weak. So there is a chance that the stronger will spill over the weaker one. That's the problem with, let's say, same channel and the cross channel. With the compact polarimetry, you have a compact hybrid polarimetry. This one, you have a benefit that you don't have this co and cross pole channel, because you acquire the information in this two channels, where one circular is transmitted and horizontally received, and then circular is transmitted and vertical received. There's no cross pole and co-pole channels. So that's also one of the benefit with hybrid polarimetry, right? So somehow hybrid polarimetry is, let's say, can be established theoretically or practically better than these four configurations, which transmits one polarization and receives H and V to, let's say, retain the swath coverage area. So that's why our focus of today's talk is on the compact polarimetry. So in compact polarimetry, compact hybrid polarimetry, what we do, we receive the information in this term. As I already explained, the RH and RB are there, and it can be converted to the covariance matrix, same as we do in full polarimetry. We multiply it with the Hermitian one, the transpose and conjugate of this matrix, and you'll reach to this beautiful, let's say, 2 by 2 covariance matrix. We usually convert it into Stokes parameter. That's one of the benefit with the, let's say, with working with, let's say, compact polarimetry things, that you can have four real components which can inherit all the polarimetric information which you acquired here. Means you are not losing any information, but you went to a domain of four real parameters. Real means these are not the complex parameters. These are real numbers, and that's very easy for us to do the mathematical things. Like if you're handling the complex number with real and imaginary part, it's really difficult to do the conjugate and all things. Sorry, to do the square root, square power 3, 4. A lot of things are there. But if you have all the real elements, it is more easier to visualize and to do the mathematical things. When you switch from covariance matrix, or from, let's say, Jones factor to covariance matrix, and then from there to Stokes parameter, you have four set of elements that can have a physical significance like this. The G0 indicates the total backscattered power. G1 indicates the power contained in vertical and horizontal component, like in this orientation, how much intensity you have. G2 gives you insight about the pi by 4 and 3 pi by 4. You can say minus pi by 4. So pi by 4 orientation and minus pi by 4 orientation component will be stored in G2, and G3 is for the circular polarization insights. Like if I'll ask you that, okay, if you have a LHCP, left-hand circularly polarized wave, pure left-hand circular polarized wave, then the Stokes parameter will be something like 1001. So that means the total intensity will be there, and there will be the fourth component, which indicates the circular polarization condition. And the other components will be zero. So usually we have a backscattered information in a partially polarized nature, and then we decompose it into different scattering mechanisms. So we'll be discussing about this. So let's talk about the first application based on this mathematical information. So we reached to the Stokes parameter. Now we'll be trying to implement that for the different applications. The first application will be, let's say, STM method, which I proposed 5-6 years back, the hybrid pole 3-component model-based decomposition techniques. And it has been modified by many researchers. Now you have, let's say, 8 or 9 variant of it. But the original one was proposed in 2017 by me, and I'll be discussing about that STM method here. So as I said, we have, let's say, we have recorded Stokes parameter, 4 Stokes parameters. Now it can be decomposed in 3 different scattering mechanisms: single bonds, double bonds, and volume scattering. You can say surface, dihedral, and volume for doing the decomposition things, for, let's say, deriving the decomposition things. Now, this is very interesting equation. These are actually this one and this one are full polarimetric, not full polarimetric. This is a complete, let's say, completely polarized component. This one and this one, and this one is completely depolarized component. This was derived from the already known, let's say, covariance matrices for single bonds, double bonds, and volume scattering. These are very famous matrices you can find everywhere, and this corresponds to the Freeman-Durden decomposition theory. So if you derive this covariance matrix in terms of hybrid polarimetry, you can reach to this 4 set of Stokes parameter for surface scattering, then for dihedral scattering, and then for volume scattering. And if you assign the weight, and let's do the sum of these 3, we are receiving this information, and we are representing this in terms of surface, dihedral, and volume scattering, which is very standard way of doing the polarimetric decomposition. As I said, these two are completely polarized. You can actually combine them together, and you can make the equation like this. This is a very interesting equation. We usually have, let's say, we call it wave dichotomy theory, which says that partially polarized wave can be represented in terms of completely polarized and completely depolarized. And there's the same thing being happened here, the completely polarized and completely depolarized. These two are combined together to represent in this way. And now you can actually solve this equation very well, because it has 4, let's say, equations and 4 unknowns. You can solve all equation, you can reach to the decomposition method. You can calculate PS, PD, PV based on these actually formula, where, as I said, FM, these parameters can be calculated from the previous slide expression, and then you can actually calculate these 4 components. Based on these components, the PS, PD, PV, this the surface scattering, dihedral or double bonds scattering, and volume scattering contribution powers are expressed in this way. The whole details of mathematics and other things you can find in these 2 papers which we published. This is the original paper, which was based on the hybrid polarimetry STM method, 3-component model-based decomposition method. And this is the recently modified method. In this year, one of my PhD student has actually modified this method to let's say, to make it a modified STM method. But you can find many, at least 6 or 7 variant in the reported literature. You can go through those papers, and if you have any doubts about the mathematics or how it is being derived, I'm always available for you to contact. So we try to validate it on real, let's say, hybrid polarimetry SAR data. This one is of the RISET radar imaging satellite data, and this is acquired over the Mumbai region, where we have, let's say, all 3 type of scattering mechanism dominant, like ocean, urban, and volume. It was very difficult to find the urban areas, because you can see I have shown this one. This one is actually the zoomed version of this part. This part is zoomed here. That's one of the refinery, Bharat Petroleum Refinery, which do the oil cleaning stuff. And you can see oil wells here, like this one and this one. And this is the optical image. This is the optical image again. This is the optical image. And these are formed from hybrid polarimetry. These are formed from hybrid polarimetry, let's say SAR-based decomposition methods. M delta, and this one is, sorry, I forgot to actually add it. It's M alpha or M chi. This corresponds to this image. These are the conventional methods which been proposed by Rane and Claude. Very famous, very prominent method. We compared our, let's say, result with these two methods, and we found that it's very nice to see if you involve the alpha, beta, and all things. We call it surface scattering models parameters. You have more better realization. You can even see here the ocean, urban, and volume are more prominently visible in the proposed method than the other one. Also, the quantitatively it performs better. We also validated it on this one. This data is not freely available for, so it was in collaboration with ISRO, and they have provided this data. But now, actually, recently they have, probably in 2019 or 20, they have released one of the hybrid polarimetry, pure hybrid polarimetry data of San Francisco Bay region. We tried to, I just tried to validate my STM method on that too. This is the M delta M alpha, and again, you can select various different, let's say, small land covers to see that how the performance works for different conditions, and we have a better, let's say, overall accuracy. It's very nice to see that even oriented urban area, we have a good, let's say, good detection of urban pixels. 68% is very good accuracy in terms of hybrid polarimetry, unsupervised method. This data set is freely available for you to download. You can download it from there, and you can use, let's say, any tools, PolSAR Pro or other, even you can use the MATLAB or other tools for reading it, and then you can implement the decomposition method. Actually, I have not added the code here, but probably I'll write you all attendee on the email sharing the code of STM method. You can try to use that and let me know how you actually interpret it. How if you have any problem, or if you need to discuss anything on that, I'll be available. So jumping to the other application, that is planetary exploration, where okay, this is connected to the previous theory which I have presented here, because we are taking some of the information, some of the, let's say, mathematical formulation from there, and we are trying to do the dielectric estimation of the lunar surface regolith. That is useful in, let's say, resolving the mystery that water ice existence is there on the southern pole region or not. Or also you can do the morphometric analysis of lunar crater based on, let's say, the dielectric estimation. So just recall from the previous theory which we established, we did these mathematical things. I already described you, and I will not be, let's say, repeating it here. So you can actually calculate all the parameters, and you can reach to this component, that is beta, because we can calculate alpha, beta, and all other parameters from this decomposition theory. Beta is nothing but the reflection coefficient. That is the ratio of, let's say, in a horizontal and vertical reflection coefficient, and beta represents the ratio of reflection coefficient. The correct word will be ratio of reflection coefficient. Why we have chosen this parameter for estimating the dielectric constant? Because it depends on real part of the dielectric constant as well as the incidence angle. So the beta can be calculated from the radar side, from the, let's say, hybrid polarimetry acquired information. You can calculate beta based on the STM method, which I presented there. And then you know the incidence angle, you can calculate the epsilon r. Just you have to reverse it and you can calculate the epsilon r. That's the whole concept for us. This concept and obviously with the results are actually published in two different transaction paper, one by me, and then it was extended for the full polarimetry by one of the PhD scholar, and he also published this just after 1 year. So we'll be discussing about the data for sure. We validated our methodology over Apollo 17 mission site. So it was very nice. This let's say this paper was of the what this the work of this paper was part of one of the project from ISRO that was on the Chandrayaan-2 data sets. But when we were doing the analysis, it was very early stage, so we are not having the data acquired over the Apollo site. So we have chosen one of the freely available data, that is the mini RF SAR data, that is also hybrid polarimetry data, and it is already publicly available to download, and that is of NASA, and that they have released a lot of data sets, and we found one of the data which was actually taken over, let's say, Apollo 17 mission. Apollo 17 mission was done between north and south massive, and relatively in a flat region. This is the path you can see here, which was followed during the Apollo mission. There, I can actually use the pointer there. And what they did during the Apollo mission, they actually collected the samples from different points on the lunar surface. They collected them, taken them back to the Earth surface, and they did a lot of experiment on the Earth-based laboratory, in the Earth-based laboratory. And they released a lot of information about it, the dielectric constant, the, let's say, the other parameters, how it behaves with the temperature and all things, the material type and other things. And we are particularly interested in these, let's say, in these samples which were calculated, collected from these points. We found these points, or we marked these points on our, let's say, radar data, the hybrid polarimetry synthetic aperture radar data. These are the locations you can see, and we tried to match the dielectric constant estimated based on our methodology with the Apollo mission sites, which was released by from the side of NASA. And it's very interesting to see that you can visualize this. This is the estimated dielectric constant, the real part of dielectric constant value based on our method, based on beta. And these are the data which was released from the Apollo 17 site from the side of NASA. The estimation accuracy is pretty high. Means you can see it is more or less matching the one which was calculated based on the radar. It somehow are somehow matching with the Apollo site released dielectric constants. The estimation error is less than 3%. So you can visualize that how accurate it was. And it was very fascinating research that we can remotely acquire the data of the surface without visiting the location, and we can calculate the dielectric that is more or less accurate to the one which was collected when they visited the site. Now, we also validated the theory with, let's say, newly released Chandrayaan-2 data sets, which is from the ISRO site. Obviously, we didn't know the dielectric constant of these locations. We have selected one of the data of Biot crater, one of the beautiful crater. You can see this is the bottom area of the crater. This is the slopy area of the crater. And this is all, let's say, ring of the crater. It's not auto-rectified. It's just as it was acquired in Chandrayaan-2 data. It's also hybrid polarimetry data. Now we are not having the dielectric constant, so we have chosen a different way. We have chosen the surface bulk density, let's say, way of comparing. We calculated the surface bulk density based on this formula. This is one of the known formula, empirical formula, which was established in 5-6 decades back. And we selected different regions. Like this one is highly disturbed region for sure because of the seismology disturbance, and also it's a bottom part. So obviously it is more impacted on based on the meteorite. These are A1, A2 are in the region of splashed out material. So splashed out material are, you can see the splashed out material are distributed over this region. These are also somehow disturbed, but not then B1, B2, and C1, C2 are the two locations which are completely undisturbed. Let's say without disturbed, so should have a higher surface bulk density. That was intuition from our side. And we tried to validate, and we found this thing that for the C1, C2, that's not disturbed area, we have, let's say, calculated the dielectric constant and then the surface bulk density. Higher surface bulk density for these two, medium for these two, and lowest for these two, as we expected, and we actually validated this. So this was of the lunar surface implementation. Just for the people who are interested in lunar surface exploration, this Chandrayaan-2 data is freely available now on this website. You can actually visit this website. You can download whatever data you want. Even they released hybrid polarimetry as well as the full polarimetry data to download. And you can download a software also. They have released the software at this website here, this website. You just need to register yourself, and then you can actually download a MISAR software that is helpful. That's a microwave data analysis software, VDAS they call it, and that can be used for processing the lunar surface exploration based Chandrayaan-2 hybrid pole as well as full pole data sets. Now, jumping to the application 3, probably I have some time. Yeah, I have probably 10, 15 minutes, 20 minutes. So we can cover this application also. That's the, let's say, military imaging and surveillance. I'd like to talk about this thing because I proposed hybrid polarimetry inverse synthetic aperture radar concept. In inverse synthetic aperture radar, the dual polarimetry and full polarimetry were already been used, been implemented, but hybrid polarimetry has not been tested yet. So for the first time, theoretically, I actually proposed it in the previous year. It was published in one of the journal and not realized practically for now, but it had some benefits. I'll explain this to you. In inverse SAR, the condition is the sensor is placed static, but the target is moving. For example, if you have, let's say, kind of aircraft which has a very high velocity and it is moving, and the relative motion between the, let's say, target and the ground play the role to form the synthetic aperture. The concept more or less is same, but this is in inverse SAR, it is pretty more challenging because you need to actually decide the IPP, that's a projection, image projection plane also, and you need to do a lot of things like however, the azimuth resolution will be improved based on the motion of the target, same as in synthetic aperture radar, where the motion is of not same, where the motion is of the platform, not the target. Usually in the synthetic aperture radar, we consider the targets are somehow static and the platform is moving. But inverse SAR is just opposite. The motion, the let's say uh, reference point is just opposite. The motion is associated with the target and the antenna is grounded. So in this case, also again, the compact polarimetry concept has the benefit. For example, if we talk about the full polarimetry inverse synthetic aperture radar, what we do, we transmit H, we receive H and V, and then we transmit V, we receive, let's say, H and V. So we have HH, HV, VH, VV, all four components together, and we combine them together and we say that, okay, this information is one entity information. Now there is a problem in combining these two. First of all, the the bad PRF, because you have a global PRF up to this area, means you to up to this time, you say that, okay, you are acquiring the data, and then you'll go for the other data acquisition. So this is the, let's say, this is your 2T is the PRT. So somehow PRF is half, so it is actually reduced. So that has the problem. It can impact, let's say, the acquisition information, and it can create the aliasing effect for fast, especially for the fast moving targets. If the Doppler bandwidth will somehow exceed the PRF, in that case, it is really problematic for us. We need as sharp or as frequent as we can actually acquire the Doppler beams. Much as we can sample, we will have a good accuracy, right? And there is a decorrelation effect, which I was saying, that you acquire the information HH and HV at this instance, and then we expect that the target is not moved up to this. Then only you can have the combination of this, let's say, scattering matrix. You can combine them together and you can consider one entity information. But this is not in the case of inverse SAR. When the target is moving very fast, it is non-cooperative and maneuvering very fast, there is a chance that at the instance when you collected H and V, the target has this type of, let's say, rotation, position, and all things. But at the other instance, when you collect VH and VB, the target probably has changed somehow. It can have a rotation, or it can have a, let's say, translational or rotational, any kind of motion. And the information you acquired is not the same, not the same from the same targets. The target, the orientation has changed, and a lot of things have changed. The surface has changed, the structure has changed, and you cannot consider these two coming from the similar scenario. And it is not a good way of combining them, from my point of view. That can create a decorrelation effect, right? Especially for very fast moving target. So the solution is you need to transmit one polarization, and when you are receiving the information, it has to be final information. It has to be final acquisition, and then you can again transmit and take the information. You can combine RHRV, you can combine HHHV, but you cannot combine HHHV with VHVV for the case when the target is very, very, let's say, highly moving. For sure, when it is static or moving very slowly, you can argue that, okay, we are transmitting the electromagnetic wave, it's very fast, it's stop and go things, and there's no problem. But in this case, it can have a problem, and there is a decorrelation effect. And also, if you are talking about, let's say, making your system more smaller towards ATR side, the automatic target recognition side, you need to have a lower data volume. And for that also, this is the compact polarimetry one, the proposed hybrid pole compact polarimetry one is more preferable than full polarimetry one, because you have a less information to, let's say, handle, and you can go for the real-time automatic target recognition. Now, obviously, the question is, okay, you did this thing that, okay, you transmit one polarization, receive orthogonal polarization. General argument could be, so you have a less information about the target, comparable to the full polarimetry. So is it sufficient to detect or recognize the target? That is one of the important thing in the military application. So we have investigated this part from our side. This is one of the data which is available freely for you, that was actually acquired under this mission, moving and stationary target acquisition and recognition, was taken from the GTRI, that's the Georgia Tech, and it was, and also Air Force site. They've acquired, they've actually recorded this information in a very controlled environment where they placed the Russian tank over a table, and they rotated the, let's say, table, and for different aspect, they actually calculated the data. It's a controlled inverse SAR full polarimetry data. And it's very good for the interferometry purpose also, because they actually collected the data from different instance in let's say in space, and therefore it based on the baseline, you can have the full you can have the interferometry concept. But for now, we are focusing on the full polarimetry. This is all about the information about the data. It is full polarimetry. The frequency band is 9.6 gigahertz. For usually for military application, we use this high X band frequency, and these are the other associated information for this. This is the resolution in feet, 1 feet by 1 feet. Now we can compare the full polarimetry based information to the hybrid polarimetry based information. First, comparison with the span, that is the total backscattered power. Full polarimetry span, you can see here, this looks like this. And in hybrid polarimetry, for sure, because of the mathematics, we have half of the total intensity than the full polarimetry. So I tried to compare by multiplying 2, just mathematically by multiplying with the factor 2. You can see this one, and this one. It's more or less very similar to each other. So most of the features, let's say in full polarimetry, are completely retained in the hybrid polarimetry condition. You can actually, we have visualized it more, let's say, deeply through the contour plot. And in the contour plot, you can see some of the changes, very, very few, like I have marked with the arrow. But more or less, I can say that most of the features are somehow retained. Now, other things, what we do is the polarimetric scattering mechanism comparison. Okay, these are same or not. This is the decomposition results generated from the Freeman-Durden decomposition method. And this is with the STM method, which I actually presented at the very starting, the hybrid pole 3-component model-based decomposition technique, which I proposed. Here's the citation for that. Okay, so you can see again the features are highly, let's say, for the mudguard, for sure there are some changes in the colors are blue and green, but other features are more or less retained, right? So and for let's say 3D imaging, we usually take the bright scatterers. We find the bright scatterers based on the clean. I tried to find these bright scatterers also through the clean and compared for the bright scatterers the span and entropy, and again the full polarimetry plot is being followed by the hybrid polarimetry plot. So more or less the information in all span, entropy, decomposition parameters, everything is somehow retained. So that's all. This is the hybrid polarimetry. This is the conclusion which I already discussed. I think it's finished from my side. I'll